So let's consider what happens if we only have two baristas and we, lay off the third barista. Now, those baristas that remain are the same. Let's say they're in the base case without training, so they have a mean service time of 87.6 seconds, standard deviation of 83 seconds. We're going to argue that the two streams are identical because all we're going to do is just reassign the workload of the third barista to these two folks. So what is this number? So in total, the cafe is experiencing 26.4 times 3, which is 78.9. And now I'm going to divide this by 2, and that number ends up being, looks like 39.6. So each of these two baristas now has a heavier workload, 39.6 customers per hour, and they remain unchanged. They're still, serving these caffeinated espresso beverages to the tune of 41.1 per hour. So let's see how we might analyze this. So again, because these two baristas can be considered independent, statistically identical, we can just analyze one of them. I'm going to just adjust this arrival rate now to 39.6. The mean and the standard deviation should, I think I need to, the mean is going to remain the same. Just confirming that it's 87.6, there it is. And the standard deviation needs to go back up. I think we're at 8.3 now. Let's just take it back up to 83. That's the base case. And without training. And then the number of servers needs to be 1 here because we're just analyzing just this subsystem. It's an MG1 queuing model, easy enough to analyze with a queuing. We're going to get an inferior estimate because of the truncation, right? That issue that I previously discussed with the normal distribution centered at 87.6. When your standard deviation is 83, this tail here is about 15% roughly, because 83 is about, 1 standard deviation below the mean. And, we know about 70% of the mass in a normal distribution lies within 1 standard deviation of the mean. So in the tails, we must have 30%, and there are 2 tails, so 30 divided by 2 would be 15%. That's how I'm getting the 15%. Again, just rough estimate. But because of this, because I'm throwing away any sample data, I'm sampling from this distribution, and because it's truncated, anytime I get a negative number, I go and regenerate a sample from the distribution. And so now, instead of being sort of all across the board, I'm limiting to just non-negative numbers. And so I am going to get a higher mean. I'm going to get a lower standard deviation because I've cut off the range of the distribution, essentially. So we're going to get a rough estimate of performance in this particular setup. But let's go ahead and run it. I'll just do a couple of scenarios for you here. So now let's think through this. There's about 40 coming in per hour. There are 50,000. So 50,000 divided by 40. Let's say I can simulate this for about 12,000 minutes. So 50,000 divided by 40. It'd be 12, 50 times 60. I'm going to just I'm just going to simulate it for 50,000. I'm not going to do the math in my head right now. Just for quickness sake, let's do 50,000 and then run that. Okay, so I actually got an exception here. And you can see that there's a problem. I mean, my waiting time is blown up crazy. And I have 99% here. This is a sweatshop, right? With these two baristas. This is just not viable. When I do the base calculation, I think I'm coming back with about, what do we get? 96.37% utilization. Really, this two barista situation is sort of, unadjusted. Whether you've got any other innovations to go along with it is really problematic, not really viable. So this is just evidence that there's some sort of overflow error. You can see what the error is, and it is that there was an agent that was unable to leave one of these ports. It actually tells you where it is. There are limits in these simulation models, and I think, for example, here, if I go back into my model and I just click on this, there's a limit of 1,000 customers lining up there. So let's just confirm that. Yeah, there it is. And what's evidently happened is, the system is so overloaded, and the queuing behavior is so explosive that, we're out of whack, and it just cannot continue. I've got an extra line that's just popped in. I just want to get rid of that. All right, so I will attempt, one or two innovations here. Let's look at the two barista solution, where we're pulling the orders. So essentially, the baristas work in a team, and they serve the orders as a team. So there's one order queue, and they're trained. So the arrival rate is going to be, can I just clear the notation here? So this is my setup, just to sketch it, just for clarity. But one order line, lump all the orders together. There are two baristas now on this team. They're trained, so 87.6 seconds mean and 8.3 seconds standard deviation. They're identical. After that, the beverages go out. This is 78.9 per hour. That is the total order load coming in to the cafe. And, they're serving it as a team of two trained baristas. So the arrival rate needs to be changed to 78.9. So it means service time is going to remain the same. That's just your 87.6. Just confirm that's what the case is. There it is. Standard deviations down to 8.3. Here, the estimate is going to be fair if we do not get a system overflow from the sweatshop effect. And here I have two servers. So let's give this a whirl. May overflow again. That 1,000 may be a crucial limitation, but let's see. The 1,000 spaces. So I'll go for 50,000 minutes. How do I know it's minutes? It's actually laid out there. See minutes. And I'm going to go ahead and hit OK. Now it crashed at about 5,000 customers. And it's getting a little better now. So I'm getting, according to this, it ran all the way out to 50,000 customers. So it actually exceeded. That was the limit. I only generate 50,000. There's a limitation in the arrival process that doesn't allow us to exceed that. So a 10-minute time in system, and there's a problem here. This service, let me just make sure I have this down correctly. It does look to be correct. 78.9. 37.6, 8.3, and 2. That is interesting. Would have expected, worse results. This is one pass, and I think what I may need to do is to run this for a shorter period of time. Let's just run it for 20,000. I may have run it too long on that, may have reduced the utilization. So let's just redo the simulation. What probably happened there was I ran it for 50,000, and a lot of that time, it wasn't seeing any additional customers. So let's just simulate it for, I'm going to just do, let's say, 25,000 minutes. Yeah, so now, you're getting the same waiting time in the system, but now it's not idle for the, the remaining 25,000 seconds. So you're getting a better estimate, and that is actually pretty close. So could this work? Yes, from the customer perspective. Can it work from the sweatshop perspective? Not so clear. Not loving that utilization number, but I leave it to you to deliberate on how to address that, if at all. Hope you enjoyed these clips. Looking forward to seeing what you're going to do with the case.